Hello. In our previous video, we looked at various systems for ranked output. Now we want to expand that a little bit in looking at non-binary proximity measures, an advanced version. Here, doing pretty much the same lecture, but doing it in 3 dimensions with colored string. We're going to try to do this with some diagrams and some photographs. So let's get started. We talked about the Cooper and Marin unified model. It came about when Steve Robertson visited from England for a term in Berkeley. And we spoke about how all that they were trying to do was to measure similarity between documents and requests. Blending the enhanced description of questions and the enhanced description of documents led to the concept of measuring the similarity of documents to requests. So, a bit of review. We looked at the representation of distance of a request from each of the documents. We had art and science, two vectors, possibilities, 2 axes, 2 dimensions, and we calculated the absolute distance from the request to document 1 to document 2, document 3, document however many. And we spoke of measuring distance between vectors, angle, measuring the angle. Now, step into the real world. Here, still a 2-dimensional representation because it's only a photograph, but it might be easier to use our imaginations on 3-dimensional space. 2 dimensions, pretty easy to imagine. 3 dimensions, still doable, but starts getting a little harder. Retrieval systems have more. They have 1 dimension per descriptor. So if there are 1,000 descriptors, there are 1,000 dimensions. If there are 150 million descriptors, there are 150 million dimensions. Let's stay with 3 for now. So we're going to have art, we're going to have science, and we're going to add to that funding. We're going to have the request be art 6, science 9, funding 10. It'll be a 3-dimensional vector space model with request. Like this. The request has the little red flag on the top, and the documents are poles sticking up without requests, and the string is tied to each one at approximately the point up the pole that they would have to be to represent 6, 9, and 10. Measure the distance pretty much the same way that we did before on the 2-dimensional, the art and science. So we just measure the distance from the request to the document for document 1 and document 2, no problem. Well, it's a little tiny bit of a problem, but not much. These are my original notes from talking with Professor Cooper back in 1981 on Model H. This is pretty much what we have looked at earlier, but I just thought you might like to see how it looked in my original version, not with the spectacular special effects of sticks and PVC piping. Said those things already. Here's a sketch of a simple example: the request, defense, budget, Reagan, Congress, Pentagon. And what we have here is the notion of vectors, a vector being a quantity with both a magnitude and a direction. And in mathematics, physics, engineering, a vector is simply a set of numbers, a string of numbers, column of numbers. Here we see an early version of demonstration of a three-dimensional vector space. What we were working on is literally embodying the three-dimensional vector space. What we're doing in a vector product space is combining the values, the numbers applied to each of the descriptors, with the values for the request, each of the numbers and the descriptors for the request. Each of those sets of numbers, the document values and the request values, is a vector. When we combine the document vector and the request vector, we get a new vector, one of a different size and one of a different direction. When we do that for all the documents, we can measure which are closest to the request, which documents are closest to the request, because the document request vectors that are largest are the closest to the request. I'm not sure that makes sense. I'm going to try to get that making a little bit more sense here. What we did is to put ourselves in a space where we had tiles on the floor, so we could measure 0 to 10 along one wall, 0 to 10 along another wall at 90 degrees, and then 0 to 10 up the wall. We'd put pieces of masking tape were the same distance apart as the tiles were. And then one person, in this case, I believe it's me, it's the request standing in the middle here. What I did is to put my string in the corner, walked the appropriate number of tiles in one direction to get art, the appropriate number of tiles in the perpendicular direction to get science, and then held my hand up the appropriate number of tile distances to get funding. Clearly in this example we're using different values than the example in the PowerPoint, but hopefully you still understand what's happening. Then each person representing a document did the same thing. They had to walk in one direction on the tiles for one descriptor, then in the perpendicular direction for the next descriptor, and then hold their hand up to whatever height the third descriptor was valued. So you can see the two people on the left are at about 9 and 10. The people on the right are in the 4, 5, 6 range. And you can see that we are literally in a three-dimensional space. Quite colorful looking too. I just want to go through this one more time. You walk out in one direction for one of the descriptors, then you walk in the other direction, one of the other descriptors, and then you go up the third dimension for the final descriptor. And that last point is the combined vector. So the point where we see each of the little sunbursts in two of the axes are the separate, and then the final one, the one at the top, is the combined, which is technically called the vector product of one of the documents and the request values. So again, for our purposes, a vector representing a document or a vector representing a request is the set of numbers representing the weights of the terms. For us, that means our request is Art 6, Science 8, Funding 9. The vector is 689. One of the documents, the vector is 874. So combining those two is a form of matrix multiplication. Don't have to worry about that at the moment technically, but it's fairly simple. We go through and multiply the value in one column with the companion value in the next column. If you have lots of documents, you'd have lots of vectors, or if you had lots of descriptors, you'd have lots of values in the vector. But it's a simple matter. It's just multiplication. When we say matrix multiplication, it sounds fancier, but it's just a simple matter of multiplication. So we multiply 6 by 8, that gives us 48. 8 by 7 gives us 56. 9 by 4 gives us 36. The total value is 140. Not unlike what we've done already. When we looked first at the the unified model. So the vector product combines weighted index record and weighted request. Here our request defense budget Reagan. You'll notice Reagan is actually a negative number. There's nothing that says they have to be positive numbers. If you really don't want something, you can make a negative number. Congress, Pentagon. And as we've done before, we have documents described in similar ways. The retrieval rule apply to each document the sum of the products of each term appearing on both the request and the index record. That's what we just did. So it looks like this: request term 1 times index record term 1 plus request term 2 times index descriptor 2, and so on. Book 1, we have the request is 42 minus 3, 4, 5, and the descriptors are 3, 2, 5, 4. So we have 4 times 5 plus 2 times 3 plus negative 3 times 0, which is going to be 0 anyway, plus 4 times 2 plus 5 times 0, total of 34. Go to book 2. do the same thing, multiply um, the values that are in common. We can't multiply if they aren't in common. So, uh, for example, book one had trident or trident missiles. Well, that doesn't appear in the request at all, so that's why we multiplied by 0. Book two, uh, 4 times 0, 2 times, plus 2 times 0, plus minus 3 times 0, um, 4 times 3 plus 5 times 0, that's only 12. So it's looking like book 2 is not going to be very high on our list. Book 3, we go through the same process, we get 24. Book 4, we get 24. So not too hard to guess that we would suggest document 1 and then a tie between 3 and 4. And if you're desperate to see something, book 2 should be the last thing you look at. The angular distance between vectors is also a useful measure of proximity. And there are different ways of measuring similarity and proximity, several different ways, and some newer methods have been developed since Cooper first worked on these. But the fundamentals remain the same. One of the reasons we might want to look at the angular distance, not the absolute distance, is that the documents might be of very different lengths, or that you happen to know that different algorithms or different indexers who work a little bit differently assign the descriptors. And this would be a way to account for that to some degree. There are other more sophisticated reasons for doing this. I just want to point out how it's done. Not unlike what we did earlier, except we're doing it in 3 dimensions. So the vector product, multiply the vector for the request by the vector for each document. Retrieval rule, apply to each document, the sum of the products of each term appearing on both the request and the index record. That's what we did. So we're just doing this, repeating what we did earlier with the rectangular representations of documents, but doing it now for the documents that are in our 3D photo. We'll come back to that to show in just a moment. So by our calculations, document 1 is somewhat closer to the request than document 2. Document 2 is not awful, but it's not quite so close. Here, what we're talking about. Good. Document 1 on the left, the request in the middle, way up at the tippy top, the little red flag on there, and document 2. Now, if you look at this just by eyeball, you can pretty well see that document 1 is closer. The angle is smaller. It looks almost only half as big as the document 2 to the request. Back for a moment. And this again from the early 80s. looking at the cosine of an angle in a right triangle. Cosine gets larger as the angle gets smaller. So we have a nice way of looking at closeness. A vector product formula looks at both the length and the angle. The cosine system normalizes the length so that only the angle matters. And this is going to be fun to look at. This is what I said earlier. If one indexer tends to put heavy weights and another one lighter weights, these will be balanced out. There are a lot of ways that the documents could be different. It might even just be in the writing style. There are a lot of things that have been shown to come into play here. So here's what this similarity measure looking at the angular distance looks like if you write it in crappy notes in the early 80s. This is the cosine vector product, and it's simply a modification of the vector product system where we did the multiplying of all the numbers, all the descriptor numbers that were in common between the request and the document. Here we're going to take the values that we got, that 200 and something and the 168, and we're going to do something special with those. Here's the retrieval rule. This could be good at a party if you want to impress people. Tell them that the retrieval rule for the similarity measure in the cosine vector product is to divide the vector product value by the square root of the product of the sum of the squares of the request descriptor weights and the sum of the squares of the index descriptor weights. Every time I sit down to rewrite something on this, I have to make sure, okay, am I remembering this in the proper order? Do that. So, the cosine in a right triangle is the ratio of the side adjacent to the angle, the acute angle, over the hypotenuse. This is just like what we did in the earlier video. So the acute angle here, not the right angle, not the 90-degree angle, cosine, represented by the Greek letter alpha, is equal to the adjacent side divided by the hypotenuse. And we know that the cosine becomes larger as the angle becomes smaller. So we have a useful, almost intuitive way of looking at the closeness of items in a graphical space. We use one dimension for each descriptor. So a 1,000 term vocabulary would use a 1,000 dimensional space. A 15 million term vocabulary would have 15 million dimensional space. Computers are handy for these. The calculations are simple. There are just a lot of them. Okay, we're going to work on this angle between document 1 and the request. When we looked earlier, it looked like that one was smaller, so we would say the document 1 is closer, but we want to have a numerical way of demonstrating that, and we need to be able to do it for more than 3 dimensions. So we're going to measure the angle between document 1 and the request. already measure. Reminder, we're going to divide the vector product value by the square root of the product of the sum of the squares of the request weights and sum of the squares of the index descriptor weights. When we say that, the sum of the squares, that's just a way of doing the division of the length of the side adjacent to the angle by the hypotenuse. That's what we did in our earlier video. We're just doing it in a fancier way with more pieces now. So the request is 6, 9, 10. Document 1 is 2, 10, 10. What do? We multiply 6 times 2, add to that 9 times 10, add to that 10 times 10. Then we take the square root of the square of the request descriptor 1, the square of the request descriptor 2. The same for all the descriptor weights that we have in there. We added those all up. And then we multiply those times the index descriptor value squared, the first index descriptor squared. Add to that the second index descriptor squared, and so on for however many descriptors we have. So the top value is 202, as we found out earlier. That's the 6 times 2 plus 9 times 10 plus 10 times 10. That's 202. Yeah, just had to check my addition there. And then we're going to take the request descriptor. The first one is 6, and we're going to square that. And then we're going to add to it the second descriptor weight, that's 9. Let's square that. I'm going to add to that the weight of the third descriptor, 10 squared. And then we're going to do the same thing for the document descriptor, 2 squared plus 10 squared plus 10 squared. That gives us an equation that looks like this. 36 plus 81 plus 100 is 217. And we multiply that times 4 plus 100 plus 100, 2 squared plus 10 squared plus 10 squared. That's 204. We multiply 217 times 204. That equals 44,268. We're taking the square root of it. The square root of 44,268 is about 210.4. So if we multiply 210.4 times 210.4, we will get to the number 44,268. So the retrieval status value then is 202 divided by 210.4, and that's approximately approximately 0.960. Again, this seems like a lot of work, but you'll notice that all we're ever doing is very simple multiplication, very simple addition, except for the square roots, and you can do that on your phone. Now if we do this again For document 2, we'll go through the same process of 6 times 10, 9 times 2, 10 times 9, and square 6, add to that the square of 9, add to that the square of 10. Hold on for a minute. Square 10, add to that the square of 2, add to that the square of 9, and then multiply those two sums. The top value, 6 times 10 plus 9 times 2 plus 9 times 10 is 168. Then we have the square root of 6 squared plus 9 squared plus 10 squared times 10 squared plus 2 squared plus 9 squared. It's 168 over 193 times 185. That's 35,705. The square root of that is 188.958, almost 189. So the retrieval status value is 168 divided by 188.958. That's 0.889. So the retrieval status value for document 2 is 0.889. And here we are looking at the document 1 to request angle. That was a retrieval status value of 0.960. Here the greater angle for the request to document 1. Retrieval status value of 0.889. 9.6 is, 0.96 is greater than 0.889. Not by a lot, but it is still greater. So our intuition, our visual guesstimating that the document 1 was closer holds true mathematically. In any real system, there are more than 2 documents, more than 3 descriptors and dimensions for each document. Have more than one request even. In any real system, there are also going to be a lot of documents with very little proximity to the request. So many documents will be either way down the list or just be 0 value. They're not even worth reporting. Here, a bunch of documents scattered around, 3 documents that are sort of close. I understand that it's a very different way of thinking than we have ordinarily thought about how close a request is to a particular document or any set of documents. You might want to try this. Find yourself a garden or a wall near a floor, 2 walls near a floor at a corner where there's a tiled floor, and just get a couple of people to hold up string. Do it socially distanced or wait till everybody's got their vaccine, but give it a try sometime. There's a lot to be said for making models to try to grasp what's going on here. It doesn't matter where you make them. Part of my point of going out in the garden, doing this next to my compost pile. I just hung the laundry as well. Just to cleanse our brains a bit, here's an image I made of some irises from the garden. to just help you relax into thinking about retrieval system models. Uh, Remember, this is not a set of videos to make you proficient practitioners of any one of these models, but just to give you a hint of what's going on behind the scenes in various models, ranging from the manila folders through the card catalog up through Boolean searching and Google. Believe it or not, the three-dimensional model we looked at with the PVC pipe and the dowels is not unlike what's going on behind the scenes in Google. They have lots of PVC pipes. That was a joke. So I'm going to stop it there, and let me know if you have any questions. I look forward to seeing some postings in the discussion area. Thank you. This is the last of the videos for this term. Thank you for watching. Bye-bye.